No. Do we see the pattern here? Or maybe we need to do some manipulating in order to see the pattern. Yeah, we should probably rewrite this one. So I have the integral negative 4x times 1 minus 2x squared squared, but it's not really squared, it's negative 2 dx. So I have an inside function raised to a power. The derivative of the inside function is negative 4x squared, or sorry, negative 4x, which is sitting right here. So the pattern is there, which means that I can integrate this thing using the general power rule for integration. What will I get? We add 1 when we integrate, right? So it's to the negative 1. It can be negative 1. N is not negative 1. Remember, the original n right here can't be negative 1. That's supposed to be a negative sign. We don't have that. We have a negative 2 here. That's fine. So it's going to be negative 1 on the bottom. And now we rewrite that to make a good-looking answer. The negative sign can just go up front. The negative exponent here sends that to the denominator. Is that it? Good. For the second one, we should probably rewrite this also. Rather than having the cosine squared x, let's make that cosine x squared. Do I have the pattern here? No, why not? Yeah, the derivative of cosine is negative sine. So if I rewrite this, cosine x squared sine x dx. If I had a negative sign sitting here, then I'd have the pattern. So I can do that, but I have to keep the expression unchanged. If I just put a negative sign on this, I've changed everything. So I have to put a negative sign out front also, so that the negative times negative becomes positive. And now nothing has changed. So now the pattern is there. So it becomes the negative out front. This turns into what? Is that it? I have to divide by the new exponent plus c. The next thing is the change of variables for definite integrals. So when we do a change of variables for definite integral, there's a great shortcut to use that makes our lives easier. It's an easy one to forget about. It does show up on the AP exam a little bit. It's not that you have to use this to get the right answer, but it is kind of a nice, handy way to shorten some of these problems. Basically, do the change of variables just like we learned how to do already. But also, change the upper and lower limits of integration by substituting them into g of x and making those results the new upper and lower limits of integration. So basically what's going to happen is, if this is your original function right here, you would let u equal g of x, and then take the derivative of u, of course, du equals g prime of x dx. So then du takes out this guy, and we're left with just the du right there. I let u equal g of x, so that leaves me with f of u here. So here's the f of u du. That's what we learned how to do earlier in this section. But now what it's saying is to take your limits a and b and substitute them into your function up here. So you'll get an answer for your new lower limit, g at a, and you'll get an answer for your new upper limit, g at b. If you do that, then all you have to do is integrate this function and evaluate at these limits, rather than having to back substitute over here and then evaluate at these limits. So you're saving yourself like 2 steps, maybe more depending on the function. The reason that this works, I'll try to show you something graphically. if I have some sort of random function that looks like that, and here's A and here's B, and I'm integrating from A to B. Okay? That's my original function. Now, if I find a new function that is replacing this function, then its graph would look different. Maybe it looks like this. I don't know. Okay? And I'm not saying that these scales are the same even. This is just a new function that mimics the area under the curve of this function when I integrate it. So if I integrate from G at A, maybe that's right there, and G at B, maybe that's right there, then this area right here is exactly the same as this area right here. That's why I'm able to do this. So all we're doing by making f of u du is we're taking this thing and turning it into something equivalent at these limits right here. That's all it is. So if you want to do it this way, you certainly can. It's a definite time saver. All right, so all of these steps are exactly the same as what you've seen before, with the exception of what is not grayed out. So this is with definite integrals. Part D down there, substitute the upper and lower limits into the equation for u. Each answer is the new upper and lower limit. And then step 2, once all x terms, the limits and the dx have been replaced, then evaluate the definite integral as normal, and then the answer is the answer. You don't have to go back. You don't have to do anything else. You're done. They're equivalent. Okay? Well, so if you want to check your integral, then yeah, check your integral. There's no checking your answer, though. There's no way you can. Unless you want to check your area that you found with the integral equation that you used. Right? See what I'm saying? We're doing definite integrals here. Okay, evaluate this integral from 0 to 1. Well, I don't really want to go from 0 to 1. I want to use this process here to show you how to do it. So the first thing we need to do is still choose a u. So let u equal what? Oh, you guys are professionals already. Now what? Okay, so du equals 2x dx. Now what? Yeah, we have x dx here. So I'm going to solve for x dx here. So I have 1/2 du equals x dx. Now if I think about it, I have the x squared plus 1 defined as u. X dx turns into 1/2 du. So I have all of the x's switched over to u's. Now I want to find my new upper and lower limits. So for the upper limit, I'll take, technically this would be g of x. So I'll evaluate at 1 first. You can write like g of 1 equals 1 squared plus 1. So that would be 2. And then g of 0 equals 1. So my new upper and lower limits are 2 and 1. So my new integral is going to be from 1 to 2. I have u to the third. I have 1/2 du. There's your integral. So now we can integrate that thing. We have 1/2 times u to the 4th over 4 from 1 to 2. So that's going to be 1/2 times 2 to the 4th, 2, 4, 8, 16, over 4, which is 4, minus 1/4. So 4 minus 1/4 is 15/4 times 1/2, 15/8. That's the whole point of this. If you are evaluating a definite integral and you find this and you get down to here and you substitute in your upper and lower limits, what you've done is you've found a brand new function and a brand new integral that will give you exactly the same area as the original function with the original upper and lower limits. So once you've found this, you're done. You don't have to back substitute. You don't have to do anything else. Do more definite integrals with U substitutions. Do you want to check to see that, make sure that this actually works? We don't have to start all over. That's right. The answer is the answer. You don't have to go back, okay? But it might be helpful if we check to make sure that this actually did work. We should get 15/8 if we back substitute and use the original upper and lower limits. So, let's try it. Let me change colors. Purple seems fun. So I still have the integral from 0 to 1. Now I integrated this thing and I have 1/2 u to the 4th over 4. Right? No, the 1/2 still stays up front. The 1/2 is still there. Oh, I see what you're saying. Right. Okay, so we substitute u back in and we have x squared plus 1 in there for u. So now it's x squared plus 1 to the 4th over 4. And we're going from 0 to 1. Okay? With the 1/2 still out front. So I have 1/2 times 1 squared plus 1 is 2 to the 4th power is 16 divided by 4 is 4. Minus 0 squared plus 1 to the 4th, 1/4. So the math works out exactly the same here. The numbers are exactly what we saw. This is a very simple example, so it seems maybe like this actually was less work, but the idea is you wind up with exactly the same answer. So when you get to more complicated integrals, you much rather would stick with this than go back to here. Okay? Because usually this math will be easier. So what should we do on the second problem then? Using the same process. So rewrite it. So we have what? 1 to 5 of negative 1/2 dx. Looks lovely. Now what? Okay. Let u equal 2x minus 1. Dx. So dx equals 1/2 du. Because of this x right here, we did not take out that x when we came up with the dx. So we're going to have to solve our u for x, which means u minus 1 equals 2x. So u minus 1 over 2 equals x. So now we can take out that. From this, we can take out that. And this is my u. So now we've written everything in terms of u. Now what? Yeah, substitute the upper and lower limits in to u so that we get our new upper and lower limits so that we can avoid having to back substitute. So I could say g of 5 equals 10 minus 1, which is 9. G of 1 equals 2 minus 1, which is 1. So those are my new upper and lower limits for my integral. Okay, so let's go ahead and write it down. We have the integral from 1 to 9. X turns into u minus 1 over 2. This mess turns into u to the negative 1/2. The dx turns into 1/2 du. I'll put the 1/2 out front, the du over here. Good. You can take out this 1/2 here. So I'm actually going to rewrite all of this. Then u to the negative 1/2 can go into the denominator. The 1/2 here can come out front. So now I have 1/4 integral 1 to 9 of u minus 1 over u to the 1/2 du. How does that help me? No. Where do you see a negative 1 inside our u? Here? Because that u minus 1 over 2 was this guy right here. So this is this.
Yeah, but when we pulled out the 1/2.
We pulled out a 1/2. A 1 times u minus 1. Okay, that was a question. No. No. This guy's actually already dead. Split. Split this up.
Oh, this is what we always get.
1/4 integral from 1 to 9 of u divided by u to the 1/2.
Which is negative.
Minus
Negative 1 over
u to the negative 1/2. So now we can actually integrate this thing. 1/4 times we need to integrate first. I don't even see a 5 anywhere on here. First of all, this is a 9. Second, we're integrating 2/3 u to the 3/2.
You only said that like 12 times. Yeah, we know this.
Minus. This becomes u to the 1/2, which means we're divided by 1/2, so it's actually 2.
9.
From 1 to 9. So would you like to back substitute here and deal with your original limits, or would you rather use this and your new limits? Personally, I'd rather use what we have sitting right here. It's less work. We already did all of the hardware work. So I need some more room, obviously. Okay, we have the 1/4 out front times. U to the 3/2, so that is 9 to the 3/2. You can cube first and square root second, or square root first and cube second. Square root first and cube second, so you get what? 27. Now you have 2/3 times 27.
That cancels down to 9.
It's 18. Minus
9 to 1/2. 3 times 2.
So we have 18 minus 6 here. That's our first part. Now minus
1 times 2/3.
So 2/3 minus 2. So it's 1/4 times 18 minus 6, 12. And then 2/3 minus 2. Negative 4/3. So we got minus negative 4/3, which is plus 4/3. So 12 plus 4/3, 13 1/3. 39 plus 1, 40 thirds.
Oh, I got this one.
You asked for trig functions, so here you go.
How did he know?
Like he's done this before.
What are we going to do here?
Well, start with the U.
Do we need to rewrite this first? Okay, so u, let u equal.
Do I have something to say? Or wait, this is where you have something to say. This is where I get confused.
Oh, it's not raised to a power though.
Okay, so it's not raised to a power. What's inside the trig function stays there. You're not allowed to change it in any way unless you use an identity or something. 2/3 x. I like the hesitation. If it doesn't work, then we'll go back and try to figure something else out. But this is the inside function here, 2/3 x. So that means that du equals so dx equals 3/2 du. Now we can run. Do you want to change your upper and lower limits here? Might as well. So g at pi over 2 equals. Good. And g at 0 equals 0. So that little bit of extra work saved us from having to back substitute. We have now the integral from 0 to pi over 3, cosine u, and then dx turns into 3/2 du. 3/2 sticks around, we can integrate. Integral of cosine is sine, because the derivative of sine is cosine. So we have sine u from 0 to pi over 3.
Now, we can make our
Sine pi over 3? Okay.
minus sine at 0. So 3/2 times 3/3.
So 3 over 4.
We should probably talk about this pattern as well. If you're integrating an even or an odd function. So there's some special things that happen with even and something that happens with odd, which you can see down at the bottom. But I need to remind you what even and odd means in terms of our functions and their graphs. So the properties of symmetry make integrating these types of functions easy. Remember what it means for a function to be even and odd. What's it mean for a function to be even? Symmetric with respect to y-axis. Which means what you see on one side of the y-axis is exactly mirrored in what you see on the other side of the y-axis. When we do even and odd, algebraically, we substitute in negative x everywhere that we see x, and we simplify the function down. And if we wind up with exactly the same thing that we started with, then the function is even. Think of this as the y-axis sitting right here on this equal sign. If a function is even, then every x coordinate on the left side has a y value that exactly matches the corresponding x coordinate on the positive side. If I draw a little graph in here, just something that looks kind of like it's symmetric probably. This is an even function. because every single x coordinate over here, like this x coordinate right here, I'll call that negative x. If I draw a dotted line up, its mirror component on the other side, and I draw the dotted line up, these two y values are exactly the same. And that's what this is saying. F at negative x equals f at positive x. Okay? That's an even function. So in this case, if this function is even, then what can we say about the area on this side compared to the area on this side? They are the same, which is why if I'm evaluating an even function from negative a to positive a, so if this is negative a and this is positive a, then that means that this area right here is going to be exactly the same as this area right here, which means instead of doing this integral, I can do this integral from 0 to a, but then double it, and I'll have the same exact answer. And there's a lot of cases, sometimes probably, that make this situation easier to evaluate somewhat. Most of the time.
That didn't sound very
Convincing?
Yeah.
Yeah, I made it sound that way intentionally. Okay, no, but if you have an even function, you can switch from this to this. And there are times where that's helpful, especially if you don't know the function. Okay, an odd function now. What makes a function odd? Origin symmetry. So symmetric with respect to the origin. That means it has 180-degree rotational symmetry. With this, algebraically, if I plug in negative x into the function, then what happens is I wind up with negative y. I wind up with the opposite sign for my y values. So if I take the opposite sign of the x value, then I get the opposite sign of the y value. Algebraically, that means I have negative f of x. So think of this as the y-axis again right here. I have my negative x values here. I have my positive x values here. If I take some sort of negative x value, I will get the opposite sign y value that I had over here. So it's going to probably be a little bit clearer if I draw a picture. I'll try to draw some sort of standard looking odd function. That's pretty good, actually. Thank you. So if we have x here, then across I'll have negative x here. Then f at x would give me this positive y value here. Negative f at x would give me this negative y value here. And what I'm telling you is that these values, if this is y, then this is negative y. Those two values are the same in magnitude, just opposite in sign. Okay? That's what an odd function does. And that's true anywhere along here. If I move this x over, find its mirror, then I go up to the function, go down to the function here, this will always be true. And it doesn't matter if the function looks like this. It can look like this instead. And then I'd have a negative x, but a positive y. But this notation here just tells me I'm changing the sign of x, which changes the sign of y. Okay? Now, if that's true, then take a look at the function that we have here. What can we say about the area from here in and the area from here in? They are the same in magnitude, but they have opposite signs. This is a negative area, this is a positive area, and they are both the same size. So we add them together, and we get 0. Yeah. So if we go from negative a to positive a, this is key here. If the bounds are negative a number to the positive number of a function, and you find out that it's odd, you can save yourself the trouble of integrating it and just say that the answer is 0. But you have to know that the function is odd, which means you have to do an analysis like this. And found out that it wasn't even or odd? And you could have just saved yourself the trouble. There's usually one question or two on the AP exam that do exactly this. Notice that the process is the same for both. In order to determine if a function is even or odd, you're going to substitute in negative x into the function. Simplify it down. If you wind up with exactly what you started with, then it's even. If you wind up with exactly the negative of what you started with, then it's odd. If you don't wind up with either of those, then it's neither, and you would have to evaluate it as normal. All right, so here's our one and only example, I think. Evaluate. What should we do? That's a good idea, considering I just taught it to you, right? So what I want to point out is this right here. Our lower bound and upper bound are the same magnitude and opposite in sign, okay? Over here, both of these had that case. So that's kind of a clue. It's something to watch out for. Like if you're watching for perfect square trinomials or looking for perfect squares in numbers in the problem, kind of the same thing here. If you happen to see the lower bound and the upper bound like this, maybe it's even, maybe it's odd. Doesn't guarantee that it is. So just because you see it doesn't mean, oh, I can just write down 0. Can't do that. You got to test it first. So how do I test this? No. No. I'm going to plug in a negative x. Change the sign of x to see what happens to the result. Okay? Let me go back one more time. See? Okay, substitute in negative x. Now we're going to treat this like a function here in order to do that. So basically I'm going to write f of negative x equals sine of negative x to the third. Is that okay? Okay. Cosine negative x plus sine negative x cosine negative x. Okay. So now how do I deal with this is the question. Like I can handle it. If it's a polynomial, that's no problem. You know, x to the third, no brainer. If it's a negative x, then it becomes just negative x to the third. Okay? But with the trig functions, it's a little bit trickier. So here I have sine negative x. The question is, if I plug negative the same x coordinate into sine, do I get the exact same answer back, or do I get the negative of it? So like for example, take a look at 30 degrees, pi over 6. The sine there would be what? 1/2. And the sine, if I reflect across, would be also 1/2. So is sine even or odd? Oh boy. Let's look at this a slightly different way. The graph of sine looks like this, which means it looks like this. Is sine even or odd? The graph of cosine looks like this, which means it looks like this. Is cosine even or odd? Okay, so if cosine is even, then when I plug in a negative x, then I'll wind up with the same y value, right? So negative cosine x is the same as cosine negative x. So this is odd, this is even. This is sine, this is cosine. Okay, so if sine is odd, then that means if I plug in negative x here, I will get negative result. Okay? I change the sign here, I change the sign of the function. Now the negative function now is being cubed. So what do I wind up with? Negative sine cubed x. Now cosine is even, which means if I flip the sign of what I'm looking at, what will I get back? Exactly the same thing. So this is cosine x. Over here, sine is odd, so if I flip the sign of x, I flip the sign of the function, which means I wind up with negative sine x. Cosine is even, so if I flip the sign here, the sign of the actual SIGN of the actual cosine function stays the same. Cosine x. what I have here is a negative negative. If I factor out the negative, I wind up with which is exactly what I started with a negative sign out front. Therefore, f of negative x equals negative f of x, which is odd. So that means that the integral of negative pi over 2 to pi over 2 of my function that I've now defined as f of x is 0.